I think this assignment's like, yeah. It's driving me insane. I put so much time into it. When I get into it, like handling the different ways that they can input it, whenever I'm like one of them, it breaks the other one, and I can't figure out a way to. I'm having both basically. Oh, I'm declaring two. That's awesome.
Yeah, that's right.
Okay.
So. I didn't do that.
You have your like push and pops inside your on it.
Yeah.
You're gonna see as I'm using the oh, wait, can you move that Steve, even when you're moving the XMS?
Yeah.
I don't think that works because SD's when you're working with two XMS. So maybe.
Right.
People like actual moving the forward and stuff, so I think that might be necessary. Could you try it down? Top and then moving the quadrants instead of the registers. Did you run out with that?
Yeah.
Well, good morning, everybody. It's just 10 o'clock in 2 minutes. We should get started. Okay, so the big ticket items are that next week is midterm week. And today's lecture will be a GDB one. It's not hard. GDB is not hard if you look at individual little subsets of the big story. On here. And then on Wednesday, we'll look backwards at the whole semester at the lecture material, not so much programming, but the lecture material, including all those numbers. The IEEE numbers constitute a big piece of that. Okay, so we're going to review that on Wednesday, and then the following Monday, March 10, here's the program itself. And the program you make can be written with things you've learned in the first 3 assignments. It won't go outside of those 3. So how do you practice for this program? Well, you make the 3 assignments. Even if you didn't turn in an assignment from the past, it's worth the practice to be prepared for the midterm program. Okay. And then number 12 is, this is a text about the architecture stuff. Including, hey, my favorite too, including heroes. Including heroes. Okay. Licenses are not included. I never lectured on those. So, but we'll nail that down on Wednesday of this week. What is included in the concept test. Okay. Oh, yes, this happens frequently. You have 2 hours. So you have to do something in 2 hours that will earn you a lot of points. Let's suppose that you work on this program next March 10, and after 1 hour, you realize I can't finish this in the remaining time. Well, you need to do this, although there's a reluctance to do it. Leave out something. Scale it down. In other words, reduce the number of requirements to less than the original and complete that much. Complete a program that does part of the specifications. And I endorse that fully. You earn partial credit in comparison, in proportion to how much you've done. So what should we call this? A scaled down program. We often talk about scaling up, but this is a scaled down program is okay. Okay, let's just make up something. Suppose you're working on this program. One of the requirements is to do data validation upon the inputs. You've done it in the past. You say, I know I can do that, but I'm running out of time. So you leave it out completely. Everything else works, and you submit it, and you get 85% of full credit. That's a good day's work. There's nothing wrong with that. What's the opposite that I see a lot of? Someone starts out to build the entire thing and they run out of time and it's still segfaulting and you got to turn in something. So they submit a segfaulting program and get 0. Doesn't count for anything. If you just drop out a few things and send in something that runs, you'll get positive number of credits. Yeah. So I talked sometimes in the past, I would say, you can send me this Chris Sawyer program. If you can't figure out the one I gave you, the Chris Sawyer program. Says happy birthday 47 times. Birthday. But in assembly, I'll put happy birthday. I think Chris Sawyer is 47 years old. Okay, and you can submit that. I think it's worth 20 points, but it's not 0. But submitting a whole bunch of hard work and then it's segfaulting at the end, and time's up and you have to submit something. So you turn in something that doesn't work and it just gets you a 0. Okay. So scaling down is a good thing. Scaled down programs. Yeah, just that's for next week. When you think of it. Who is Chris Sawyer? What did he do to get in our homework? Chris Sawyer is a programmer of games. He built the game that will never be reproduced in the lifetime of the earth. He built Roller Coaster Tycoon in 100% assembly language. 3 years for one person to build about a million lines of code. That's not going to be done again. Okay, so he goes on the heroes list for the concept day. Let's see, what else do I have to tell you about before we jump in? Oh, yeah, for the test. The test comes first. It's next Monday. You're responsible for your own electricity. So experience says somebody's going to come to me the next day after the test and say, the electricity went off in my house at 11 o'clock while I was working on this program. It's not it's not my laptop, it's a tower machine, and I couldn't finish it. But later that day, the electricity came back on and I finished the program. Can I submit it now? Because it's really great. Would I say? No way, man. I'm not taking that stuff. Okay. Yeah, I don't know if that's true, but it may be the trick where you pull this electricity gimmick in order to get 6 hours of extra time to work on the program and then tell the professor, hey, it wasn't my fault, it was electricity. Okay. So what happens? Your laptop doesn't boot the morning of the test. Uh, this gimmick's been tried before too. No, you're responsible for that. Having a laptop with a charged battery, if that's your machine of choice. Responsible for electricity and or equipment. So what do? I don't know. Go take the test. Leave home, take the test in the Cal State Fullerton Library. They have good electricity and it's pretty good assurance it's going to be on the whole time. Go to any Orange County library. They have good electricity, they have good Wi-Fi, it's all free, and their reputation is the electricity doesn't go off. Okay, so I no longer try to filter through which of these are good accidents and which are just fakes. But I've gotten over the years, I've gotten all kinds of strange questions, strange excuses for not submitting the program. You know what they do? You know what they do at the Orange County Assessor's Office when you have to pay property tax? Property tax is due December 10 of every year. You go to the website and it says you may pay by electronic transfer of funds. If our server is down, we're going to fine you for being late 10%. On a $1,000 tax bill, you pay $100. If their server's down, not if yours is down, they say, we don't care about this electronic stuff. You still owe us the penalty. Take care of your equipment, everybody. Okay, let's go on to GDB. Apply to XMM. Okay. Well, the XMM, any one of the XMM registers, 0, for instance, has 128 bits in it. And we have been dividing it into half and using 64 bits over here. And the SD signifies these on the right side. That's usually called the low side. And this is high over here. Okay. Every time you write move with an SD, it says you're operating on the low bits of a register. XM. 30. Okay. The other bits remain there, but nothing happens to them. That's what everything with SD is. Square root, SQRT, SD, X, M, 14, X, M, 15. Takes the square root of the low number in X, M, 15 and puts that square root in the low number of X, M, 14. And we're not going to use it, but these are good instructions. Change the SD to PD, and then it does the same action on both registers. That will make two moves. The low end of 15 moves to the low end of 14. The high end of 15 moves to the high end of 15 in the same number of clock cycles as the one back here required. It does parallel processing. When the instruction is the same, this is not true parallel processing. True parallel processing, we're running two programs doing different code. This is the same code on two different data items. So be it. Okay, so it's possible to carry this to the ultimate. You can cut it in half and then cut those in half and then cut those in half. And you have 8 registers of 1 byte each. Okay, this picture. 8 registers. GDB is going to do that in a few minutes. What could you store there? You could store an ASCII character number between 0 and 255. It's 0 to 255. Okay, to accommodate all this subdividing, there's a series of frames that I'm going to put down right now, frames. These attached to XMM registers, and we'll see how it works. B2 double, B4 float, B2 int 64, B4 int 32, B8 int 16, B16 int 8, and a very unusual one, U int 128. So this is supposed to be, and it is, a description of how the big register is subdivided. For instance, here, the 4 means 4 individual numbers. And the 32 means 32 bits in each of the 4. Okay, so we can look at XMM registers under any one of these partitioning schemes. This is what we've been doing most of the programming this semester, is treating it as having 2 numbers. We only use one of the 2, and they are type double, the traditional C++ meaning of double. Okay, so this is easy. Okay, so how are you going to? I'll do it live in just a few minutes. P slash, let's take F. X, oh, don't forget the $sign. X M M 0 dot V2 underscore double square bracket 0. That's going to show us the data in the low half, the 64-bit on those. Here's the picture of it. It's going to show us the data in here. It's 64 bits. Its index is 0. Index over here is 1. So we'll go back to what, and that's what it's asking for here. Here's the index number. The other choice is a 1 at that position. Okay, and we could look at, so how about floating point numbers from C++, X, M, 8, V, 4, float, brackets, 2. Because there's 4 of them, they're indexed 0, 1, 2, and 3. So this would pick out the third from the right. Is it 0, 1, 2, and 3? It'd pick out this number and show it to you. And doesn't make sense to do all these, but let's pick out something. How about type int? In programming, int count. Okay, so it would look like P/D $sign X M 5. Just pick something. V 4 dash int 32 square brackets, doesn't matter, 1. Okay, so that would show it as a decimal integer. The data that's in the is in this register number 1. So it would be here. Okay, and you can leave the indexing off, and it'll show you all 4 of them. Just endless number of ways you can view the data. So how about as an unsigned integer? $sign X M 5 dot V4 int 32. And if I leave off the indexing, that 32, then we see all 4 numbers. And the last one doesn't divide it into subregisters. Let's do it right here. P/D $sign X M 5 dot UINT 128. That will use all 128 bits and form a decimal integer and show you that integer. And you already know you have lots of choices. You could do it as an unsigned number. We could do it as a hex number. We could make it as, I don't know if you can use, it says int here. I don't know if it'll allow floats. We'll try it in the next few minutes and see what happens. Okay.
You say what the last command does again, that one.
This one. Yes, it takes the whole long register and does not subdivide it in any form. This is a 128-bit register and a bunch of bits, and then it applies the algorithm, say, to show it as a decimal base 10 number, or as an unsigned base 10 number, or as a hex integer number, or this one I have to find out, or as a float number. I don't think that should work because that's 128-bit floats. They have a plan in place for what the stored exponent will look like. It's not 11 bits, it's 15. We'll find out. Is that one what this does? Okay, I have a little program set aside just to do this. Let me put it up here. Okay. Let's share the screen. Oh, oh, thanks, Catherine. I'll have to fix that. Okay. Then let's see, we sharing this and then we go to here. Okay. Is this the one I was using? I don't think this one runs. Let's try. Embarrassing. Okay. /rg.sh. Oh, I guess it's okay. Warning is not an error. It just says you created this, but you never used it. Why is it here? Okay, so in here, you should glance with your eyes just for 10 seconds to see that there's no error messages in that section. And there aren't. Okay, so let's move this here. Let's break the main points. And run this. And it started to, whoops, I lost the focus. There's the stuff. Anyway, we're interested in XMMs. Let's try P / float. Why did I lose the focus? P / float $sign XMM 2 dot V 2 underscore double and we'll put a bracket, we'll put an index with it. That's very huge number. You see the mantissa there times 10 raised to the 252. So it has 252 decimal digits in this float number. So let's do it again. What if we leave off the index? Okay. There are two numbers in that register. Both of them are humongous monsters. Okay. Well, let's try just an experiment. What was that? What I was going to try? Well, let's try the P / X $sign X XMM2 2.UINT 128. Okay, so I'm asking for that in hex. That's an integer. Okay, what is it in decimal? base 10 integer. That's a very big integer for base 10. And here's the one I wrote on the piece of paper. I wasn't sure what it would do. If we ask, see, 128-bit floats don't exist yet. So this should be here. Yeah, okay. It doesn't know how to, there's another algorithm to convert bits into 128 bits into a floating point number, but it's not implemented on this computer. Okay, what was some of the, let's try something that's more common. Type int is a 32-bit integer. Let's suppose you're working with 32-bit integers and we wanted to view what was there first in decimal. Dollar sign, R, not R, X, M, pick something, 8, dot, V4, underscore, int, 32. And let's leave out the indexing and we'll see all of them at one time. Now, isn't that strange? Okay, there's 2 6s and 2 zeros. I guess it's not strange. So now, in your mind, can you see all these leading zeros? And then at the end, it says 1100. Okay, if that goes to a float number, that's a subnormal number, very close to 0. We'll try it. A float number. That, yeah. The 6 is very close to 0. It's 8 point something times 10 to the negative 45. That's close to 0. Okay. Well, let's go take the same register and view it not as little ASCII numbers between 0 and 255. That would be V16 underscore 8, int 8, 8. And then let's go over here and make it say U, unsigned integer. There should be 2 6s. Yes, there are. The previous 6 is still there. Well, what do we cut this into pieces? There's 6. Are there 16 of these? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. That would be that much would be, if you cut it in half, you'd see that. And then if you cut it in 4s, you'd see this much. And if you cut it in 8s, you'd see that. And then cut it in 16 little pieces, you see that. And how can I demonstrate it's the same data? Let's take it as combine them. Take this 8 and these are 16s. And it shrunk because the unit size is 2 bytes. So 6 is stored in a 2 byte part of the register, 2 bytes, 2 bytes, 2 bytes, 2 bytes. Okay, so what if you make it into 4s? This would be 4. This would be 32. And let's go back to 8 of, no, 2 of them. 64. Okay, the two pieces are 64-bit integers, and it's 6 and 6. Well, what we did do is, well, does this make any difference? 6 and 6. Leading zeros are dropped in GDB. So where you see 110, there's actually 61 leading zeros, and then this number is there. Did I illustrate all the combinations? Floats and count. Floats only work on 32 bits and higher. Let's Q/L. 32 bits and higher. That would be V8. This, okay, so V8. No, let's try again. V4. Sorry. Yeah, 32. No, not 32, but you don't write the 32. Then some X. Okay. Two float numbers. Yeah. 0, 4. As integer, you're supposed to change this to INT 32, and then change this to decimal. And there's the same data, same set of bits, but shown as integers, 2's complement integers. And 2's complement integers. Well, bigger integer would be 64. And 2 of them. And it's those two set of bits, 32 bits each, is combined into one collection of 64 bits. There's its decimal value. And I'm wondering, I don't know, but I think, let's see if we ask for it to appear to show in the float. 6.9, 6.6. I have no idea. Okay, it is 6.6 in the, so there's 2 of them here. I keep omitting it. The one on the right is here. The one on the left, the high end, is here, which is 0. Okay, I think I'm finished. We have a few minutes left over. What if we try to change the value of one of those? It's done by set $sign XMM 0 die V2 underscore domain square brackets, the one on the low end equals 4.5. You think that changed the value of that register? While we're at it, let's do the one right next to it. Make this one a 1. And this one, negative 37.9. So we want, those are float numbers, P slash F, dollar sign, X, M, 0, dot, V2, underscore, DOU, BLE. And here. Okay. There's a change of a register. And what if we wanted to look at them in hex? Is this an easy hex converter? Dash X. It's not bad. Here is this exponent is a nice one. It's in the area of 0 to 10. And sure, that's 4.5. But this one starts out with the letter C. C has a leading 1. Leading 1 says that this number is going to be negative. And therefore, it's C is 1100. If we took away the leading 1, I don't know. What, 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 that's not. Oh, yeah, it becomes a 4. Think of C. It's in binary, it's 1100. If you take away the leading 1 and change it to 0, it reads 100. That's 4. Okay, so let's do one more here. The set command is the key to making changes, except when you come to arrays, and it looks kind of messy. Okay, so let's set dollar sign. Where X M 0 dot. I was going to change the one on the on the far right that at index 0, V2 underscore double E at 2. Actually, it counts from 0 to 1. And that's a bad spelling. E-O-U double brackets equals 37.9. Okay. And then let's put in the first place. 0. In hex. And then in float. So, and I lost. Where did the 39 go? The 37. I thought I put a 37 in here, but I can't find it. The negative 37 is still there. It's still here. It accepted this with no complaints.
I'm sorry.
Oh, it's number 9. That was a misprint from back then. Thanks. The 9 and the 0 on the keyboard are next to each other. Okay. Okay, there's positive 37. And I wanted to show you that in hex, it was like a C had been modified. Okay, so Let's do this. Okay. Yeah. The P. Okay. The leading zeros. That's too bad. I can't make sense out of it. There's a leading zero in here. That's 0, 1, 0, 0. That's a 4. Okay, for the exponent. But what was this one? So here is XMM 0 as double. Well, we'll try. Okay, here's the letter C. 1100, and then when I modified it, the one on the left dropped out to 0, and it changed to positive number then. Okay, I think you already know on things of changing values in XMM registers. Things. Do we have to enter it in base 10? Let's find out. Set $sign XMM0 dot G2 underscore double. What happens? I think it will BLE bracket 0 equals. Okay, let's go 0x 400 or 44 0. Okay. That's around 1,000, I think. Let's now look at it. So P slash D $sign X and 0 dot V2 underscore INT 64 INT 64 square bracket 0. And look at it. I'll show it as a decimal integer. No, that didn't work. That really didn't work. Oh no. Well, that's decimal. I assigned it in hex. Let's see if it's still in hex. No. It's not what I expected. I expected to see this number stored over here in index 0 of XMM0. It didn't work. Instead, I got this thing. I wonder what. Zero. That's 10. And now we look at and uh, I don't know the answer there. This is uncommon to assign values in hex, but it should work. Last attempt. Let's go set $sign XMM5 dot V2 underscore let's go INT 64 at 0 equals a number 0x4 a the hex number, and there's a little this print here 0 0x, that's what I need. Okay, we're putting it in the low end of XMM5. Press enter. No error messages. Now we want to view that exact same thing. Take this away. And P/D. We got 74. Is that 4A? I think it is. Okay. It's 4A. 4A in hex is 74 in decimal. That time it accepted it. I think the cause of the problem was mixing int 64 with double. It's true they're the same number of bits, but it didn't. This one up here didn't work. So we'll leave it go. If you stick with the same frame, then it did work. Here, this was placed there with int 64, and then we can view it with int 64, same frame. In decimal, and it's okay, and in hex, it's okay. Well, what's our clock? 70. It's 10:50. Let me stop this. Anybody have questions for me? How do we know that XMM2 and XMM8 represent fifth number in an array? Sullivan, the question, I don't have the context. What is A5, XMM2, and XMM8? I don't know enough to be able to answer your question. We're going to end here. I'm just confused how we move that specific. What specific SSE register to use? Oh, okay. No, I think so. No, for this demonstration today, I just picked ones at random to show you how the frame specifies within a register which values you're working on. See, if someone just wrote well, I was just picking registers at random. The issue is like setting a value, $X XMM5 equals 3.7. This doesn't make sense. You need a frame to specify where in XMM5 you're going to place this 3.7 number. So for the last 20 minutes, the demonstration, I just picked XMMs at random, 8, and then put a number in there. But in order to do that, you need to specify let's go ahead. If you're working in doubles, there's double. Number 0. Now this is expecting that if you're assigning a value, it would look like this. Set equals 3.7. If what I just learned is if you're putting an integer into that same place, M8 V2, you should do this. And then that worked. It verified itself. I tried to use this again with an integer and it didn't accept it. But this time it did work. So those two large ones have something special. It's back here. These are the same bits, but you expect to see floating point type out of here, and you expect to see integers types out of here, unsigned or hex or whatever it is. Okay, and then these two go together. It's sort of, if you're looking at float numbers, you'd inside the register, you'd use this one. But if you want to look at those as integers in the same bits, then you would use the one here. Int, there's a 32 attached here. Okay. That was the last little experiment. All right, on the concept test, I'll ask you some questions about GDB. We'll discuss that on Wednesday of this week. Just what kind of questions. The story is not finished with GDB. I personally had trouble. Arrays in assembly and arrays in C++ are quite different. And the GDB one reveal this, uncover it for us. Most arrays in assembly are stored in the stack. The stack holds array data. You declare an array of 3 numbers, there'll be a place where it is. 7, 2, and 5. That's in C++ and C. In assembly, those 3 numbers are not in the stack. They're far away in the heap space area. In fact, heap isn't supposed to be drawn in the stack form. It conveys the wrong idea that it's stacked up. It's just one linear mess. ASM. So those numbers would be scattered down here in heap space as a 5, reading a little Indian, and then a 3, and then a little Indian, then a 7. But this is assembly. Does it differently. And it depends what you're debugging. But if you, for assembly, we'll see that ourselves. So the storybook on this GDB is not closed yet. We're still going to do some more after the midterm. Are we done? Okay. We're done. Okay. This might be on your midterm test. There's so many things. I don't know how much could be fitted into this test. Okay, I hope you're enjoying macros. Macros are like functions with less restrictions. That's a good reason to know that macros exist. When you call a function, there's a lot of overhead. Some caller function says double A equals find, and it passes B and C. You know, that operation is really slow compared to the rest of your code that's running. There's a lot of overhead happening. It's creating new space on the stack. If this is C++, it's creating new space on the stack. It has to count the number of bytes that find function has declared locally. It increases the stack size by that amount. And macros are much easier. It would be the name of the macro, and you name what you're passing to it. If you're inside of assembly, like most of you are, you would set a register here, R8, RCX, and R15. Yeah. There's no overhead. It doesn't create more storage on the stack. It doesn't do anything. It just accepts these inside the macro. This one is known as %1. This one is known as %2, %3. Okay, so macros have their usage. People tend to prefer functions, I guess, for portability. It's nice, but macros have a lot of plus points on their side. What they can do. I'll leave it at that. So you're supposed to build some macros and put them in the include file. I had in mind that all those pushes are BP and its move statements or BP RSP. By the way, that's there because of this messy problem of calling a function. The RBP is at the back, but of the back of someplace new. And so this accommodates the function call. Anyways, it'd be nice to have all these pushes, RCX and so on, in a macro, RDX. And then in the future, you could simply call the macro with no parameters. Backup, GP, general purpose register, or just backup, or backup general purpose register. Okay. No parameters, no overhead. It would just do all those pushes for you. And then you need another macro, which would be restore. Restore GPR. And it do all the pops for you. And it cleans up the code. It looks prettier. And once the macro is debugged fully, you never go back and look at it. So, okay. I think lecture is finished. So when were we reading this? Yeah. So leave on. Keep in mind, there's only 2 instructions. They're officially called commands in GDB that let you look inside of data, look inside of registers. It's P followed by a single letter, or it's X followed by 3 parameters. This is how many. It's like a positive integer. This is the form, and this is size. So Okay. Most of the time we use this one, but if it starts to involve addressing and addressing our pointers, then this is the tool to use. If you have the address out of memory, let's see. Well, that's just take a now. Some parts of memory are protected, and they won't let us look at it. But if I just had some memory address 0xFF874090. There's some leading zeros that are missing. Okay. We could look at what's stored there with the X command. P won't do it. I want one number. I want it to be in hex form, and it's going to be a 64-bit number, and it's at address 0xFF874090. Okay, so this command will go over there to memory and bring it out for you. And if you wanted to see 10 in a row, 10 consecutive ones, you just change this to 10 XG and a memory address. That's okay. That's who does this? Forensic sciences working in law enforcement do this, and virus hunters. Viruses carry a signature, and you want to search through gigabytes of memory trying to find this signature. They do that also. Okay, I'm just going to be here, and you're welcome to use this nice room. And have a great day, everybody. We'll see you on Wednesday.